Welcome back to Chem 4300. In this video, we're going to continue Chapter 11 on wave mechanics, and we're going to build on the material what we learned earlier in the chapter, where we learned how to construct the position and momentum operators, which operate on the wave function in the position basis. And we're going to use those operators to construct other types of operators to solve more and more sophisticated physics and chemistry problems. And so, most obvious thing that we're going to move on to from position and momentum are the energy operators, the kinetic and potential energy operators. Excuse me. Now, the kinetic energy operator we can construct very simply by replacing the momentum, which shows up in the classical expression, with the momentum operator. And that gives us this expression here. Now, as written here, it would apply very easily to the wave function in the momentum basis, but we want to apply it to the wave function in the position basis. So we're going to use our definition for the momentum operator, minus I h bar, partial derivative with respect to x, and we're going to use that in this expression here to construct this expression for the kinetic energy operator as applied to the wave function in the position basis. Now, the potential energy, as you know from our work earlier in the class on classical physics, will depend entirely on what kind of problem you're looking at. And that same is going to be true, of course, in quantum mechanics. And solving the Schrodinger equation can be really easy or really hard depending on what the form of that potential energy function is. Just like the problem was hard to solve or easy to solve depending on what it looked like in classical physics. We're going to look at some simple cases starting out, and then progressively they're going to get a little bit harder and harder in terms of the form of this potential energy function. The simplest case is probably this one here, where we look at, say, an electron, a particle trapped in a one-dimensional box where the potential is infinite outside the limits of the box. So the box goes from 0 to L, and it has a zero potential inside and an infinite potential outside. This is called the infinite well potential. Another case we could look at, we'll look at later in the course, is this is the harmonic oscillator potential energy function. And here again, we just replace the x with a hat, x hat, and we get the potential energy operator for that particular problem. Now, generally speaking then, when you add up the kinetic energy and the potential energy, you have the total energy. And in quantum mechanics, that operator is called the Hamiltonian operator. And if we were going to write it out for, and say, as applied to, say, the wave function in the position basis, we might use this. But if we're using the wave function in the, in the momentum basis, we would use this. In the position basis, we would use this form over here. Now, if I take the Schrodinger equation that we learned in the last chapter, and I write it out again, you'll see that this part here matches this form here for the Hamiltonian operator. So we can write the Schrodinger equation more compactly with this definition of the Hamiltonian operator, and we can write it as E psi is equal to H psi. So the Hamiltonian operator operating on the wave function will give back the wave function times the total energy. All right? And additionally, you see, remember, there was a time-dependent part, and if we look at this expression here that we got by making the substitution, we see that the Hamiltonian operator can also be defined as the I h bar times the part of the partial derivative with respect to time of the wave function here. So we have these two definitions for the Hamiltonian operator in quantum mechanics. So let's look at some of the issues, that more general issues, then we'll look at a specific case of solving the Schrodinger wave equation. Now, when our potential energy depends only on position, we can generally do this same trick that we did before, which is a separation of variables. So we can write our wave function as the product of a spatial part and a time part. And if we take our Schrodinger equation and we make that substitution here for these separate parts, and then we expand it out, well, on the position dependent side, you can see that the time dependent part just sort of slides through these terms over here, and we just have the second derivative with respect to position of the position dependent part, and then the potential energy operator operating only on the position dependent part. But then, of course, on the other side of the Schrodinger equation, we have the derivative with respect to time, and when we plug that in over here, then you see the time dependent part gets taken, we get to take the derivative of that, and the position dependent part slides through there. So taking all this together, I can rewrite it in this form, and what I've done is I divided both sides by the inverse of the total wave function, and this allows me to put everything on the left side that depends upon x and everything that depends upon time on the right side. And of course, this is again a familiar strategy we've done before. When we can do this, we know the only way to make this true is to have this equal to some separation constant, and which in this case is going to be the total energy, which is a time-independent quantity. It's our separation constant. And so now we can take this two equations, two ordinary differential equations equal to our separation constant, and solve this side and solve this side to get the solution for these two different wave functions that make up the total wave function. So here are my two uncoupled ordinary differential equations. We'll start with this one over here, the time-dependent part, which is fairly simple. And you can get, right away, you can see that this one has a trivial solution, which is this e to the I minus I et over h bar. And when you plug that back into the total solution, where you multiply it times the yet-to-be-determined position-dependent part, we get this for the total wave function. When it's in this form, like this, we have a wave function that's what's called a stationary state. And the reason it's called a stationary state is that if you calculate a probability density from this wave function, that is to say, you multiply it times its complex conjugate, the time-dependent part, you see this part appear, this Euler's term, where you change the sign to make it the complex conjugate. When this part hits this part, they cancel each other out. And all you're left with is the spatial dependent part. There's no time dependence left. So when it's written in this form, the probability density that you get is independent of time. So that means that all observables that you calculate from any kind of operator expectation values with this state is also going to be time independent. So if your wave function has this form, then you have what's called a stationary state, and the probability density is independent of time. Now remember, we're dealing with linear differential equations, so you may have solutions which are linear combinations with these, in which case you might not have a wave function that's that your stationary state is not going to be, your probability density is not going to be independent of time, and so we won't have operators and expectation values that are time independent. But if we're in this state, in this form, then we have a stationary state. So keep that in mind. Now let's turn over here to the other differential equation that we got, and this is just involving the position-dependent part, and this is what's called the time-independent Schrodinger equation. And we're going to be spending practically the rest of the semester solving this equation here. This part we've actually done, and we're pretty much done for the rest of the semester on this side of the board. It's this side where we're going to spend all of our time this semester now. And you might notice that there's no I in this. There's no square root of -1, which means that all of these solutions are going to be real solutions, whereas these solutions over here are complex. And so let's take a look at this particular problem. Let's start with the simple infinite well problem. So here's our infinite well problem. Here's what the potential looks like. It's infinity over here, and 0 here. So there's no potential energy when it's inside here, okay? And we want to figure out what are the stationary states that are inside this well. All right, let's start. So we'll take the Schrodinger equation, and we know the potential energy inside the well is 0, so we can get rid of that part. And when I do a little rearranging, I can turn it into this form where I've defined a variable k, where k squared is equal to 2me over h bar squared. So that's just to sort of get rid of all these terms we're carrying around, but it's also very useful because this k is going to look very familiar to you from what we did in the chapter on classical wave motion. This equation is something you've seen already. You've actually solved this for the boundary conditions that we're looking at here. We have boundary conditions where the wave function has to go to 0 at the ends, at x equals 0 and x equals L. So with those boundary conditions, the solution to this differential equation are going to be of this form here, where k now can only take on values of n pi over L, where n are integers 1, 2, 3, and so on. All right. Now, with this constraint on k and the relationship between k and the energy, you can see that the energy now when I do this equivalence here, the energy can only take on discrete values, which are going to be given by n squared h squared over 8m L squared. So the energy now becomes discretized, just like K became discretized. And these are our energies for each of our stationary state energies. These are the normal mode energies for this problem. This is just like the classical one-dimensional wave for like the guitar string that we were solving in the classical wave chapter, right? So the energies that we're looking at now in this quantum mechanical problem are given here, and you can see how their spacing goes with the value of n, and here's the absolute value of the energies, and here's the gap between those energy levels. So this n is now something we call the principal quantum number in quantum mechanics, and you can see that those specified as a function of n, the energies. Now the really interesting thing here is that the lowest energy is not zero. Now think about what we're doing in this problem. This is a classical problem where we were doing a particle that was trapped in a box, a one-dimensional box. You can easily imagine that that particle could be sitting in the box with no velocity, no momentum, and zero energy. The potential energy is zero because the potential energy is zero inside this box. So a classical particle would have a lowest energy that would be zero. Whereas in this quantum mechanical problem, the lowest energy is not zero. It's actually some value of h squared over 8m L squared. And that's a consequence of this wave-like property associated with the particle. This lowest energy is something called the 0-point energy. This is something that happens for every bound quantum state, that you can't get to a zero energy like you would in a classical system. There's always, in a bound system, some 0-point energy, and this is a consequence of the particle's wave properties. You also see that these energy levels, spacing is increasing with n in this picture here. So let's then look at the wave function. So we looked at the energies here, and now let's go back to this wave function and finish the job, so to speak. And what we want to do is we want to make sure that our wave function gives a proper probability density when it's squared. So we know that our wave function squared and integrated over all space should be equal to 1. If I plug in the form of that wave function that we just had, then we have this undetermined b. And of course, if I look up the integral for this, I get this for the integral evaluated between those limits. I get b squared L over 2, and that has to be equal to 1 for a proper probability density. And so that gives us our value for b and our final form for our wave function. So we've now solved for the energy of this system, and we solve for the wave functions. These are the stationary state wave functions, the normal modes of this problem. And here we have the solution. Now you remember that any wave function, the particle inside this box can have any kind of wave function that's a linear combination of these guys. So any linear combination of these will also be a valid solution. So generally speaking, any wave function inside this box will be some linear combination of these normal modes, these stationary state wave functions, which will have some unknown arbitrary, some unknown coefficient here, which we could decompose with some kind of Fourier series, for example. But this is very much like again, the string where we pulled the string up, we created some initial state, we created some initial superposition, or we created a superposition of normal modes that would then vibrate with time. And assuming there was no damping, then it would just continue with that distribution of normal modes. So here we have the same kind of amplitude here, except that's describing the different stationary states that's contributing to the state of the electron inside this box for any arbitrary wave function. So that's it. We solved the problem. We got the wave function. We got the energy for solving the Schrodinger equation for a particle, say an electron, trapped in an infinite well potential. So that's it for this video. In the next video, we're going to look at probabilities associated with this wave function.